For today's quiz, we have an AC power supply, a very long wire that is going to be coiled around this massive coil. It's a ferrite coil, and an ammeter. We'd like to know is if this is 7 volts and the resistance of this coil is 7 ohms, how much current will flow? This is what your quiz looks like. As always, write your explanation as detailed as you can and list your confidence. Typical student responses are really just one. All students are going to say, well, a coil is just like a wire, and wires have resistance. It's a long resistor, and they'll end up redrawing this just like this. And they'll say, well, if I have 7 volts and I have 7 ohms, I can simply use Ohm's law, and I can kind of do that in my head, and I think it's going to be about an amp. That's the response we get. And by the way, this is a really good first shot. Let me write this out. We can end up saying that V equals our I R, and that works for RMS AC just as it does for a resistor using DC. And we can simply say I is going to be our V divided by our R, and our 7 volts divided by our 7 ohms. Even without a calculator, we can say is 1 amp. And that's a really good thought. So that's the response that we always get from students. The students have calculated their current that's going to be going through the circuit, and we might as well verify this. First thing I'll do is I'll put my meter on 1 amp. So I'll pull this out. I have to put it on at least the 10 amp scale. And that's AC, so I'll put it down at 10 amps and I'll plug it in. My power supply is already plugged in, and I'll simply connect the circuit. And we get 0. Well, maybe something shorted out. Or maybe it's not anywhere near 10 amps and that scale can't read it. But we said it was going to be 1 amp. The next scale down I have is 200 milliamps. But this is reading 0 as if nothing is going through. So let's try the next scale down, the 200 milliamps. And I should be able to do that because it didn't show any milliamps here at all. So I'll go to 200, and then I'll put this lead into the milliamps, and lo and behold, I have 4.5. Not 1 amp, which is 1,000 milliamps, but about, 4 or 5 milliamps. How can that be? What's happening here is that we're using Ohm's law and assuming there's only resistance. But there was a hint here. It says L equals 11 henries. And that should have given us a little pause to say, wait a second, I wonder what else is going on here. So to be fair, the students might not have known about this next thing that's similar to resistance, but it's called impedance. And we use a letter Z for that. And it looks just like Ohm's law. So I can write it as our voltage equals our current times our Z. And Z is going to be impedance. Maybe we should explain that. So let's take it up here and let's talk about impedance. Impedance, given the letter Z, and Z is going to be equal to the square root of our resistance plus, and now we have what's called reactance. We've got inductive reactance, which is happening here, and we also have capacitive reactance. So I'll make an X, L, minus Rx, and that's going to be C. And then we need to square this right here like that, okay? And that is going to be our resistance and our reactance. So maybe I could put those down here. This is going to be our resistance. And this is going to be our reactance. And reactance is really about how the capacitor or the coil is reacting. Remember, inside this coil, I have current that's flowing because it's AC. And as it goes through this set of loops around this ferrite core, I'm going to try and build a magnetic field. But remember, this is 60 hertz. It's trying to change its magnetic field 60 times a second. So it starts building, and by the time it tries to get built up in this massive inductor, it doesn't really have enough time to complete that cycle. And so it's starting to grow, but then it's going to switch back the other way, and it's going to end up impeding the current that flows. And that's what this is all about. So we call this our inductive reactance and our capacitive reactance. We're going to ignore the capacitive part because this is not a capacitor, but we'll have some problems later when we try and measure these things. But for now, let's just go with this. So I can end up saying, well, maybe I need to put down here what our capacitive and our inductive reactance. We're just going to ignore that term for right now. We can say that our inductive reactance is equal to our omega and our L. L is going to be the inductance. And we can also say where omega equals 2 pi f. And that's the frequency. And if you're thinking, wait, omega, that's for things that rotate, it's the same thing. So I can end up saying here, we can have our inductive reactance is 2 times our pi times our frequency. And in the United States, we use 60 cycles. And then I can have my L, which is right here. I do this calculation quite often, so I know that 2 pi f is going to end up being 377 1 all over seconds. Now, we're going to multiply that by our number of henries, which is 11, which was given on our quiz. And you'll see that this is going to be a rather large value. Grab a calculator. So now I could put 377 times our 11, and we get a whopping 4147. So our inductive reactance, 4147. And that's going to be 1 all over seconds times henries. Which should probably help us understand what the units of a henry are. So if we're talking about an inductor, we can say that, let's just box this in so we know that we already have that answer right there. I can say an EMF is going to be negative, whatever our inductance is, with our change in current all over our change in time. Now we can rearrange this. And by the way, that's just the same thing as saying voltage in our units. So I could say our, let's take and get L alone. So I can have, and let's not worry about the negative. We'd say L is really going to be our voltage times our delta T all over our change in current. Now let's see what the units are. Remember, I'll put units in parentheses. So here I've got inductance, which is going to be a henry, is going to be a volt times a second all over an amp. So if I end up having 1 henry is a volt second over an amp, I could rewrite this as just the units 1 all over seconds. And then I'm going to end up having a volt second all over an amp. That's what I got here. Notice seconds cross out one another, and then I'm going to be left with a volt over an amp. And as we saw over here with Ohm's law, I could rewrite this as saying, well, this can be rewritten as R can be thought of as our voltage divided by our current. So our volt over an amp is going to end up being R ohms. So you could see that we have a volt over an amp, just like we had a volt over an amp equals an ohm. So all of this is equal to 4,147 ohms. So if I take my formula right here for my Z, and I want to find the total amount of current, first thing that I could do is I could say, well, I could put 7 in here, and I'm going to get 7 squared is 49. Not that large of a number. But look, when I take this value and put it in for here, and then square that, and we're assuming that I don't have any capacitive reactance right now, that is going to be a giant, giant number. And when I have a giant number on this side, and I'm going to add a smaller number and put those together and then take the square root, I'm essentially just going to end up with that number there. So our Z here is effectively just going to be nearly completely from our inductive reactance. That 7 ohms that I have here is almost nothing at all compared to this massive number that I have right here. So our Z is really just going to be our 4147. You know what? I'll put it in the calculator very quickly just to see if it changes it. I'm going to put my 4147 in here, and I'll square that. And then I'll add our 7 squared, which is 49. Add those together and then take the square root. And it still gives me almost the identical value. So I'm just going to put that in for Z. And I can solve for the current here. I can say my current is simply going to end up being our voltage divided by our Z. And I could say 7 volts divided by 4147 ohms, and that's going to be our I. Put that in my calculator, and then I'll multiply that by our 7, and I get about 2 milliamps. So our I here equals 0.002 amps. Now that's not exactly what we're saying here, because this is a little bit more complicated than we make it out to be. And that's what I'll show you right now. But before that, I just want to point out that if we just think of resistance in AC, we are missing a very important complex part called this reactance, either capacitive or inductive. And it's to our peril. I mean, you can see that this circuit is absolutely dominated by the reactance and not resistance. Even though they are both going to have the same units, they're fundamentally different. But how we measure that is one of the problems that we're going to have to tackle right now. What I'm going to do to help us measure our resistance in the coil and our capacitive reactance, or at least we're going to try, is I'm going to unplug this so I can use this same meter. I can take this off, and I can unplug that, so I'm in good shape. But this is actually going to allow us to measure the resistance. So I'll put this onto our 200 scale for our number of ohms, and then I can take the rest of my meter and hook it to the other side of this coil. And remember, it really is just a very long wire. So if I put this on, I get about 7 ohms. So measuring the resistance of a coil, it's really not that big of a deal. Now, I will caution you, there's a battery inside this meter, and we're putting it onto a coil we got to be careful that we don't get a little bit of a shock here. So I'll take this one off. I think we verified our resistance here of our 7 ohms. But we made the claim that our capacitance or capacitive reactance is essentially 0. But how do we go about measuring that? And I'll just give you another formula here. For this capacitive reactance here, so I could say, I think I have a little bit of room here. I could say my capacitive reactance would be 1 all over my frequency times the capacitance. I actually have a capacitance meter on a multimeter. Let me grab that and let's see if we can hook it on. This meter, I can turn it on, and I have a farad scale right here. Just hook that right here. I have 2 yellow leads that I need to connect them to. They go into a special set of ports. And I'll hook the one to the one side of the coil and the other to the other side of the coil. Pull these over and hook them on here. And I get 141, and that looks like microfarads. So I should be able to put that into here. Now, if I were to put that for my capacitance here and multiply that by 377, I'm going to get a very large value. Here's the problem. You can't do this. This is not a capacitor. Remember, this is a wire, just a long wire. So how do I measure the capacitance? Well, this is where you got to be careful, because your meter will tell you, look, it's measuring. And it is. It's measuring something. But it isn't like the capacitance that we think. That turns out to be very, very difficult. So you got to be careful. Just because your meter can read something, that doesn't tell you that you can actually use it. At some other point, we're going to show you how we're going to use phase angle and a few other techniques to get the capacitive reactance. But it's a fair assumption for now that because this is a coil and not a capacitor, we can ignore that portion of the equation for right now. All right, let's give you a real-world example of when you might use this. And we use them all the time. If you've ever been in an office and you see the fluorescent light bulbs, you're going to need a ballast, and here's why. Now, by the way, we're trading over to LEDs, so we're not going to be using these in the future as much, but for a long time, they're going to be around. And these fluorescent bulbs are just gas tubes. Let me draw one. What this gas tube is going to do is, first of all, establish a very high voltage across each side. So these are going to require thousands and thousands of volts for these fluorescent bulbs. And then we call these ballasts. And a ballast looks just like a coil that's in a rectangular form. So it's just like the coil we were talking about before. Think of this as just having a massive amount of wire coiled in there. And I've got lots of different colored wires. Let's talk about why we need so many wires. First of all, in order to jump from one side to the other, and we're going to put some electrons that are going to jump this tube, and through quantum mechanics, they're going to give off particular frequencies of light. And we can powder coat the inside with different phosphorus to give off white light. But in order to get the electrons to jump in the first place, I need to boil them off. So I'm going to use one of these sets of wires, especially an old school type of ballast, that is just going to be a heater. And it's going to end up boiling off some of these electrons. And these electrons are going to feel this massive voltage potential, and they're going to start traveling one way. And as they knock off other electrons, the big positive ions are going to be coming the other way. When they recombine, they give off light. But here's the big thing that you need to know is a gas is not going to be conductive. So I can have tens of thousands of volts of difference between them. Nothing's going to flow. But as soon as I start to get some electrons to flow and some positive ions, this acts just like a wire, and this whole system would short circuit and everything would burn out immediately. So why doesn't it? Well, we need something that's going to limit the amount of current there. And that's what a coil does. A coil allows us to get that voltage at first, but once I start getting some of that current to start flowing, then I'm going to be asking it to change its magnetic field very quickly, and it can't quite keep up, and it's going to act just like resistance, but it's going to be inductive reactance. So the reactance is going to limit how much current flows through this bulb, and without that, these would instantly, within probably a tenth of a second, simply burn out. So that's just one of the many applications that we use these type of coils for. And occasionally you need to change your ballasts. You still have these in many schools and offices. You might see the maintenance people changing these out because occasionally they'll burn up. So that's a real world application, and that's your quiz for today. Thank you for watching another Idealized Science Institute video. We are a nonprofit organization. If you like what you've seen, be sure to like and subscribe. And if you want, leave a comment below. It's helpful to us. If you can financially support us, go to our website and hit the donate button. If you can't, simply by sharing these videos with other teachers and students in your life will be helpful. While at our website, you'll find that we have our Idealized Science Institute book that'll help you engage your students in dialogic discourse. There you'll also find we have a podcast where we break down educational research. We also have long-form lessons. If you're a teacher, you can watch these and go in the very next day and enact these. Along with this, we also have many other resources, including more quick quizzes. So thank you for watching, and we hope to see you in the next one.